over here. So anyway, I thought we would start today by talking. This week we're going to be talking about regression and using multiple independent variables in regression. So as kind of a recap from last week, what's the purpose of regression? What are we doing? What?
Predict.
One
word.
That's absolutely right. To predict. And what are we trying to predict?
Something of interest.
Yeah, we're trying to predict why something isn't the mean, right? Like, if we know absolutely, you can think of a regression model, of a regression analysis, as different chunks of information. Here, are you guys taking notes? You're gonna have to take notes. I'm recording. If you want to take notes, you can. So you can think of like your different predictors. I think you're better off just listening, to be honest. There's a historical record. The whole. Once everybody's here, we can. Is that door open right now?
It is. Yeah.
Okay. So you can think of a regression model as being some sort of outcome, whatever the outcome is, and each predictor in that regression model being a little bit of information about that, right? A little bit of how we can understand why that thing isn't just at its mean. Because in general, if we know nothing about something, our best guess about what a particular score or what a particular amount is for any given variable on that outcome is the mean, right? And those predictors provide information about why something isn't the mean, right? So there's this great story from the economics literature. So in the 80s, there was this graduate student, and his name was Ted Bogle. And so Ted Bogle was going to graduate school in Princeton, and he was really interested in money managers and how money managers are able to make people more money. And so, anyone know what a money manager does? What their goal is? Yeah, make people money. Like, the idea, though, is that you pay this person. They take your money, they invest it in like stocks that they pick, right? Stocks and funds, or maybe they build a fund based on a variety of different stocks, and they're saying that they can outpredict the market, right? That they have got some knowledge that allows them to outperform what the average is, right? Now, our market is based on, I mean, we use a benchmark of we can't really measure the market, and so the way that we measure the market is we say, like, okay, let's take the top 500 companies, and let's see, like, how those top 500 companies are performing, and based on that performance, that's what we use to gauge how our market is doing, right? And so this guy was like, let's see if we can figure out what aspects of money managers increase their performance above the average, right? And there was actually a study in the 40s that tried to look at this and said, that it's unpredictable. You can't predict what's going on. And so what we really need is just to have a fund that is just nothing but follows the S&P 500, and these have actually become very popular now, but at the time they weren't very popular. Anybody know what they're called? Called index funds, right? Because they just follow the market index, right? So anyway, at the 40s there wasn't one of these index funds, and they were considered like un-American, right? Like, you got to beat the market. That's the whole purpose of being American. So anyway, this guy, Ted Fogel. Ben Fogel. I'm sorry, not Ted Fogel. Ben Fogel. Come on in. He starts looking at the historical record of money managers, and he goes back all the way to 1960. And from 1960 up until the early 80s, he had the performance of thousands of money managers for 25 years, and the goal was to find out what predicts whether a money manager beats the market or not. And he couldn't figure that out. But what he did find is that almost no money manager ever beats the market, right? So basically, you are paying somebody money to invest your money, and they're giving you a worse return than you would get if you just invested in some sort of, if you just
Index
invested
fund.
on your own on an index fund. There we go.
Where were you?
Yeah, 2 minutes ago. So he concludes by saying, like, yeah, we need to have an index fund, and he finds this 1940s article that says we should do this, and he creates at that time the very first index fund, Moses, right? Moses. You know
Yes.
what it was called? It's not Noah, right? It's Moses.
Yeah. I mean, Noah, Abraham, Jesus. I've got them all.
Do you know? So Ben Fogel created the first index fund, and it was called. Anybody know? It's called Vanguard, and Vanguard is actually became like a powerhouse amongst it still is. It's still like one of the biggest trading firms out there. Now, when Ben Fogel was trying to start this new index fund, he was seeking capital, and he went and pitched this idea and showed his research to all kinds of investors. The goal was to get $150 million to start this index fund. He got 11. Nobody wanted in. Everybody's like, no, this is a waste. You're just like using the average. Like, we're not going to make anything off the average. But the truth is, across time, the average just grows, right? Like, if you look at the stock market grows. And so he started this index fund, and the index fund started doing very well. And obviously, he made a firm out of it. In 2008, there was an economics conference, and there was a hedge fund manager there. Anybody know what hedge fund managers are? Anybody know what a hedge fund is?
I feel like they're similar to mutual funds.
They're similar to mutual funds, except that mutual funds are trying to identify stocks that are going to go up, right? And hedge funds are trying to identify stocks that are going to go down, right? They're hedging their bet that the market is going to do what the market does, and it's going to be volatile, right? And so hedge funds bleed little amounts of money constantly while funds increase. But when you bet against the market, all kinds of people are willing to take that bet, right? And so when there's a decrease, when there's a drop, hedge fund managers make tons of money. And so they will bleed. A drop means huge money, and then they bleed again, and then a drop means huge money. And the idea is that across time, that little bit of bleeding is no comparison to the large amount of gain that you get every time there's volatility. And if you think about the market, and you think about volatility, you think about data in general. If we're talking about ups and downs, deviations from the mean, what are we talking about? Yeah, we're talking about variance. And so hedge funds are essentially betting on variance. You have two different types of funds then, right? You have an index fund that's betting on the mean, and you have a hedge fund that's betting on the variance. And so variance is really important if you can predict that variance, right? And hedge fund managers are full of big brain people with PhDs in mathematics and mathematical physics and so on and so forth that believe that they can predict the market. They can predict when these things are going to happen. At this conference in 2008, or it was late 2007, this Ted Seides was there, and he was a major hedge fund manager at the time. And one last name, Warren Buffett. We know who Warren Buffett is, right? Like, nobody's probably heard of Ted Seides or Ben Fogel, but we all know who Warren Buffett is. I think right now he's maybe the second or third richest person in the U.S., not in the world. There's some big Russian oil magnates that make a lot of money. But anyway. He was giving a talk, Warren Buffett was, and he said, was our door open? I think we're all here. Can somebody close that? Warren Buffett said, hey, I will bet $1 million that I can pick a better stock portfolio, a better fund than anyone else in this room. I'll put $1 million on it. And and he was specifically pitching this to a group of hedge fund managers, right? And Ted Seides was in the audience, and he was like, I'll take that bet. And so in late 2007, they made this bet, and what they did is they each put $150,000 into two different funds, a fund that Warren Buffett built and a fund that Ted Seides built. And Warren, Warren Buffett just chose an index fund, almost identical to the Vanguard fund, right? Which means he's just going to follow the mean. He's just going to stick right with the market. And of course, Ted Seides tried to beat him. Now, an interesting thing happened in 2008. Anybody know what? Yeah, we hit a recession. And guess who was flush in that recession? Ted Seides. So Ted Seides saw an increase of about 20% in that first year in his fund. And Warren Buffett saw a decrease of 45%. So huge loss. And I don't know if any of you had any, probably didn't have any investments in 2008 while you were in high school or junior high. But I did, and I lost half of my retirement, right? It was brutal.
I had a friend, his family, same thing.
It sucks. But anyway, so that first year, Ted Seides had a decisive kind of win over Warren Buffett. 2009, though, Warren Buffett came back. He didn't recoup all of his 45% loss. Ted Seides had a small gain. 2010, Warren Buffett came back again. Ted Seides had a small gain. And over time, they ended the bet last year. They ended it in 2 years ago, 2018. So it ran for 10 years. Now, at the end, they were going to donate all of the money that they made in these funds anyway, so it didn't really matter. But Ted Seides' approach resulted in, across time, a 45% increase in his initial investment 10 years ago. Which is pretty good, right? However, Warren Buffett's was a 120% increase in his initial investment, just following me. It's because you can't really predict the market, and when you can, you just get lucky, right? And when you know nothing, when you have no information, the mean is your best possible predictor. So in regression, the idea is there are deviations around the mean, and our goal is to say, like, okay, here's the mean, here's our intercept, right? This is the average, and then can we add information to this that's going to help us understand why something isn't at the average? Does that make sense? Good. All right. So this chapter we talked about a couple of different things. We are going to start by talking a little bit about, actually, two concepts. The first concept that we're going to talk about suppression today, and we are going to talk about redundancy. So in the video, I talk a little bit about suppression, and I talk a little bit about redundancy. What is redundancy? If we're coming up with a definition, what is it? Nobody?
The extent to which variables overlap in the explained variance on another variable?
Yeah, the extent to which variables overlap in the explained variance on another variable. It doesn't even have to necessarily be the explained variance on another variable, right? It can just be the extent to which variables overlap, right? So if we have two variables, actually, let's do it. I'm sorry, this chalkboard screams, doesn't it?
Remember this.
So we have three variables, and we have a bunch of different ways to think about the variance in these two variables, right? So we've got colors here. We've got this right here. And this is just the variance that x1 accounts for in xy, removing any overlap that x2 has with y, right? And any overlap that x1 and x2 have. We also have this piece here. I've never used this chalkboard before, and I had to go and find chalk this morning. Wasn't the easiest thing to find.
Find it in a museum.
Walmart did have some chalk. So we have this portion right here. Walmart has everything. What
This one left.
No, just
I got this
chalk
one
in a
here.
museum.
Yeah. Oh, gotcha. I thought they were being like dead serious, like I would have. This is the variance that's overlapped, or the overlapping variance that we have just between x1, x2, and y, right? This variance actually is really important. It's interesting. Later on in the class, we will want to look at that variance and assume that that variance is the interaction of these two variables predicting this. It's actually not what it is. In fact, the interaction of these two variables predicting this winds up technically being a third variable, which we're not going to worry about. But that third variable is not this. That third variable winds up being a different share of variance in here altogether. This actually, oftentimes, when we try to break out these variances, because variance is nonlinear, we can actually get a value for this variance, and quite frequently it's negative. And so, I shouldn't say quite frequently, but occasionally it is negative, which is mathematically impossible. It should not be negative. Why should it not be negative? Variance is squared, and it has to do with an overlapping variance across three different variables. But we're not concerned with that variance just yet. We do have a name for that variance. Anybody know what the name for that variance right there is? So before we go there, we have this piece right here, right? This piece of variance. It's the overlap of those two. And this piece, in addition to this, that overlap is redundancy. Redundancy is the extent to which x1 and x2 are the same thing. The extent to which x1 and x2 are redundant. Exactly. We have this other piece over here that is specific to redundancy within the context of a regression model, and that is when our redundancy overlaps with our y variable variance, and that is called, anybody know? Starts with an M. Multicollinearity. That means this piece over here is just called collinearity. Yeah, absolutely. So collinearity is the extent to which x1 and x2 overlap, and multicollinearity is the extent to which x1, x2, and y, or however many predictors you've got in there, right, overlap and need to be partialed out of your total variance. Now, an interesting point, this variance right here is R, right? But it's not the full R, it's something else. In our regression model, it's beta, right? We're going to come back to this R in just a little second. This is also a type of R, but this would be beta x1. This one would be beta x2, right? X2. And so from this, we can see that x2, beta x2 is actually this right here, just this portion of variance divided by all of the potential variance on y. Beta x1 is this portion of variance divided by all of the potential variance in y, right? You'll notice when we do our regression models that our beta x1 and beta x2 do not map on perfectly to the, when we talk about correlation, like if we just had two variables and we have this piece in between them, and it's not like, at least it's not like fingernails, right? But it still is uncomfortable to
Pretty
listen
close.
to. Yeah. This, between two variables, is our zero order correlation, right? And so we wind up getting 4 different types of correlations when we run a regression model. We have a zero-order correlation, which says that like here's just the relationship. And so somebody walked me through here. If we wanted to know what the zero-order correlation between x1 and y is, what is it here? The blue and the pink, right? Assuming all of this variance and all of this variance, right? So that's our zero order. The beta is this portion, assuming all of the y variance, right? So there's 2 of our 4. We then have something called so our book calls them partial and semi-partial correlations, right? Stata will call them a partial and a part correlation. Partial stays continuous, but so there's a shift between part and partial depending on the software. Like I believe Stata calls it partial and semi-partial. Are partial and semi-partial. For some reason, SPSS likes to use part. But anyway, it is a part of the partial correlation, right? So let's talk a little bit about what a semi-partial correlation is. A semi-partial correlation is the correlation between x and y that includes this portion, but partials out this amount of variance, right? Oh, I'm sorry, it does not include this portion. It's this portion, but it partials out this amount of variance. Does that make sense? And so when you are dividing this, you are dividing this by just this in order to get your partial correlation, right? I'm sorry, it is both of these pieces, partialing out just the independent portion of x1. And so you're dividing both of these by this amount. The part correlation is dividing just this portion, partialing out this, so it's this over, again, this amount. So it's the same on the denominator, but the numerator is changing. It's getting smaller, right? So knowing that the numerator is getting smaller, you can actually put these in order. You'll know exactly which one is going to be largest to smallest working across, right? The zero order will always be largest, right? After that, your beta should be the next largest, right? Then our partial, and then our semi-partial. And these are, I mean, it's important to look at these because when we start looking at regression diagnostics, you're able to say like, oh, well, once this thing was added to the model, then we can see that the reduction was largely due to covariance associated with x1 and some other variable, right? Or it wasn't due to x1 and some other variable. It was due to x2 and y, and that affected x1, which is another problem that we have in regression. So we have this portion over here called redundancy, right? And redundancy can lead to something very interesting. So if we have let's say variable like this, and we have x, we have y, and we have some sort of beta weight here, right? And then we add a new variable to this model. Let's say that we see that there's a positive relationship between x and y, okay? And then we add in x2, and x2 is highly redundant with x1. Does that, right? Now we have some independent variance here. We have a whole ton of what? Multicollinearity, right? And then we have a little bit of variance here. And what can happen is, especially if this takes up even more and more variance in y, or this does, you just get lesser and lesser and lesser amounts of variability that you can explain. And we see something interesting. We see that this x variable can do one of two things. It can go from statistically significant, right? Or, even crazier, it can completely flip signs. So we see a correlation between these two things is positive. We enter a regression model and it's positive. And then we enter this other variable that's highly redundant and it flips signs. This is a special case of redundancy called suppression. That's a suppression effect, right? So in the literature, you will see suppression effects all the time. And sometimes suppression effects are completely spurious, right? They just happen. We don't know why they happen, or we may not know why they happen. Other times they're not spurious at all. Other times there's a very good reason for having some sort of suppression effect. But what you see in papers is people will run their analysis, something will flip signs, and they'll say, oh, probably a suppression effect. And that's where they stop, right? And it's like completely useless in a scientific paper. If you have a suppression effect, then this is just my word of advice. If you have a suppression effect, try and think about why you might have that suppression effect, right? Like, okay, so x1 and y are related very strongly. And when I add x2 into this model, which is also strongly related to x1, the sign flips. And that might be because there's, a lot of overlap with x1 and x2, but in the variance that's left, what we aren't thinking about is this other piece of what x1 is, or this other piece of what y is, right? Almost all of these variables have some sort of multi-component thing to them. And so then you can hopefully offer some sort of hypothesis. And why is it good to do that? We're just going to throw it out there. Why offer some sort of additional hypothesis about x1 and x2, or about suppression?
By doing that, you're kind of differentiating the point of those variables, because otherwise, if the two variables are fully suppressing each other, then they might as well be one variable.
Yeah, so it does do that, right? It says like these two things are not perfectly overlapping, but even more so, it offers theory someplace to move in the future, right? It offers, like when you think about what's going on over here in a regression model. This is a beta weight, this is a beta weight, this is nothing. What is all of this? Unexplained variance, and the other word that we use for unexplained variance is?
Future research.
Oh yeah, error, right? We just call it error, like it's error variance. And so oftentimes we will, I saw this great talk, there's a multidimensional scaling guy named Don Hedeker, and he gave a great talk one time, and he said, one person's error is another person's career. One person's error variance is another person's career. But yeah. So anyway, the idea is maybe you can drive like some new kind of, like you push research forward by saying, look, we found this weird thing, and it could be because of X, right? Like you are hopefully, since this is your research and your data, and hopefully you're in a spot to offer the best guess about why that happened. All right, we're going to keep doing this, but we're going to shift gears just a little bit because we try and represent this model graphically, right? And the way that we represent, actually, before we do that, when we talk about regression, we are saying that y exists, right? We can measure y, we know what y is. And in order to predict what y is, we're adding some sort of overlapping circle to y, right? We're adding an x1, we're adding an x2. And in the verbiage of regression modeling and statistics, we say that y, I see this said wrong all the time, which is why I'm saying it here. Y was regressed onto x, right? And I know it sounds weird that you say y was regressed onto first, but we always put the dependent variable first when we're talking about regression models, right? So this was regressed onto, and if you read some of the papers that do this correctly, right, they'll say like y was regressed onto age, sex, and income or something, right, to control for covariance and demographics or something along those lines. And so when you see it like that, it kind of makes more sense. But just be aware that the dependent variable should always come first. The exception is if you're saying, so you can kind of use regressed as predicted by, right? And so you could say y was predicted by blah, 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 blah. But if you're going to use predicted, you can also flip it around and just say sex, age, and income predicted were used as predictors of or something along those lines, right? If it makes more sense in your head to draw it out that way, to write it out that way, the same way that you would actually write it out here, then you can do that. One last piece of suppression or what of redundancy is actually something that we look for in data all the time, and especially in causal modeling of data, right, which is mediation. And so there's a big question: how do you tell if something is redundant versus something is just a mediated effect? Mediation, what is mediation? Anybody know?
I think of it as sort of like an explanation for like mechanism or how something works.
It is. It's a mechanism for how something works.
Oh, wow, exactly.
It is. So I like to think of it like this. Mediation is the doorway that one variable has to walk through to get to the other variable, right? So mediation is a doorway. You're going to hear me say this all the time. Mediation is a doorway. Moderation is a volume knob. And so...
Didn't roll on the tongue.
So, when we're talking about mediation, what we are saying is that one variable predicts another variable, and that in turn predicts a third variable, right? So technically, what we're saying with mediation is something like this. We have this variable predicting this variable, and this variable predicting this variable. That the reason that this leads to this is because this is associated with this. However, if everything is measured at the exact same time point or what have you, then what you actually, and if you just did, in mediation, if you just did a zero order correlation, so you can see that like x1 in my like simple model here, they don't overlap, right? Now, if these two do not overlap at all, that means that if I do a simple correlation, what should the correlation be? It should be 0, but it's never 0, right? It's this x1 and y. They do overlap, right? Like if you do a simple correlation, these things do overlap. And so what you're really saying is like x1 and y are passing through this door of x2. That's why they're correlated. That's the whole rationale. I'm just like stepping on it now. I did this before you guys actually showed up. So anyway, the way that we test mediation, and we're going to do this today. We're going to talk about this today. Is there are so many ways to test mediation. We're going to get into the weeds on mediation in this course, just FYI. This course could really just be called an exhaustive exploration of moderation and mediation because we spend way too much time talking about it. But they're two of the most important concepts in psychology and especially in regression modeling. And so the first paper, the most prominent paper that was published on mediation and moderation was by these two dudes, Barron and Kenny, right? And Barron and Kenny wrote these basic steps to test for mediation. Anybody familiar with the Barron and Kenny steps? No? So the Barron and Kenny steps say, first you have to establish a relationship between x1 and y, a positive and a statistically significant relationship between x1 and y. Later research has shown that that actually isn't necessary. You don't have to establish that relationship, and there's research by David McKinnon that suggested that sometimes this really is the way that mediation looks, right? But not always. In fact, most of the time, this is the way that mediation looks. But the first step is in the Barron and Kenny method is saying like, hey, x is related to y. The second step is saying x is related to x1 is related to x2, right? The third step is saying that x2 is related to y. And then the fourth step is saying when we enter x1 and x2 into the model simultaneously, x1 is no longer a significant predictor of y. That's called full mediation. You also have something else called partial mediation, right? And that is when x1, the value of x1 decreases in contrast to, or once x2 has been added to the model. Then after we do this, you get these regression slopes, right? So we're going to have like, if we draw these out as variables, we have y, we have x1, we have x2, we have the covariance of x1 and x2, this, right, the extent to which they're redundant, and they are both predicting y after removing that piece of it, right? And so we can actually get, oh wait, I drew this wrong, didn't I? My bad. I'm drawing mediation, I just drew like a straight regression analysis. But, I mean, technically it is a straight regression analysis, I guess. The way that we in order to test this in the Barron and Kenny way, we actually have to have x1 predicting y here, right? Oh, I'm sorry, predicting x2. We were missing that one. And so we're going to get a beta weight here. We're going to get a beta weight here. We're going to get a beta weight here. And the way that we test for the strength of that mediated effect using the Barron and Kenny approach is really simple. We actually just multiply these two beta weights. So we're looking at, essentially then, running out of space here, a model that looks like this. x1 predicts x2 predicts y, and the product of these two slopes divided by the pooled standard error of these two slopes, right? It's called the asymptotic covariance of the slopes. It's not, we'll talk about that. We're not going to talk about it today, but we'll talk about asymptotic covariances, which is really the correlations not between the variables, but between the slopes. Divided by that asymptotic covariance gives you a z-score, and that z-score, if it crosses, what is our threshold for z-scores? It's an absolute value of, yep, go ahead and say it, Angie. 1.96, right? If you think about a normal bell curve, 1.96 is our cutoff for a statistically significant effect of 0.05, right? And as long as the product of these two divided by their standard error is greater than 1.96, we say that we have a significant mediated effect. Does that make sense? All of this is more complicated than it needs to be on the chalkboard. It becomes far simpler when we get to the data. So let's take a 10-minute break. When we come back, we will dive into the data.
No, that game's not fun.